Thank you for the introduction. So my name is Pablo Martinez, and I'm a PhD student at University College Dublin. And I'll be presenting the paper with the title Incipient Slip Detection for Rectilinear Movements using the PapillArray Tactile sensor, which has been nominated for the Best Student Paper Award. So first, as an introduction, some motivation behind this work. So as we all know, the human hand is capable of performing complex manipulation tasks with ease. And this is thanks to the mechanoreceptors in our skin, which provide us with tactile information, such as an object's shape, weight, or texture. And without this feedback, even the most simple manipulation task would become very hard. So on the other hand, robotic and prosthetic grippers, they cannot perform these textures manipulation tasks with such ease. And this is in part due to the inability to send these tactile parameters. So therefore, tactile sensing technology is essential to allow robots to be able to adjust their grip force and find this optimal force, so they don't apply such a high force that the object is broken, or such a light force that they drop this object. So we want to bridge the gap between human and robotic dexterity, and a key factor in this manipulation is the ability to detect slip. So in this paper, we developed a slip detection algorithm using the PapillArray Tactile sensor, which I'll present here. So the PapillArray Tactile sensor is composed of an array of silicon pillars, which are resembling the papillae of the human epidermis. And these different pillars, they have different heights. So this is going to promote the occurrence of incipient slip, which means that some part of the sensor is going to slip before the others. So some part of the sensor, in this case, the outer pillars, which are the shortest one, are going to start slipping before the center pillar, which is the tallest, which will be still in contact to the object. So in this paper, I used the sensor here in the bottom left corner, which is a 3x3 array of pillars, but we are now working on deploying these algorithms onto this new sensor that I just built, which is a 5x5 array. And this tactile sensor it gives us the 3D force and 3D displacement in each of these silicon pillars. So using that data, we'll see how to develop these algorithms to be able to detect this incipient slip. So moving onto the methodology, this is the test rig that I designed and that I built in the lab. We're running our test, and we have an hexapod, which is a 6 degrees of freedom robotic stage. And on top of it, we mount this tactile sensor. And then we tell the hexapod to move upwards in order to touch this acrylic plate. And then, as we are seeing now in the video, we displace laterally in order to force these slips to happen. And we have a camera at the top that is tracking the tip of each of the pillars. So our objective here with the camera would be to be able to have a reference of when these real slips are happening, so we can compare our algorithm detections. And we run a total of 90 tests with 5 different set compressions, 6 different tangential velocities, and 3 different directions. So as I mentioned, we wanted to determine the reference slips from the camera tracking. And here in this video is an example of how we did it. So we see now the tracking dots are turning green when they get in contact with the acrylic plate. Then the hexapod will start moving in the upward direction, and we're going to be able to detect the slips first happening in the outer pillars, and lastly in the center one. So how did we do this? So actually, to automate process, we just selected these rectangles, and then by cropping the images and applying Otsu's method, we could obtain these precise points. And then we track these points using the Kenneth Lucas Tomasi feature tracking algorithm. And then we did a camera calibration so we can obtain the pillar tip position. And then we wanted to detect this instance here. So when there's an abrupt change in this position, so we define our moment of slip of our reference slip when this slope of this line is at least 75% of the tangential velocity of the hexapod. So our definition would be that we are detecting as a reference slip when these pillar tips are moving at the same speed as the robotic stage. So now moving on to our algorithm detection. First, we wanted to detect when each of these pillars is in contact using this sensor data. So we used a very simple method, just using the set force. So we just applied a 0.1 Newton threshold to determine when our pillar is in contact. And then to detect our slip, what we did was to use the velocities of this pillar. So as I mentioned, we can obtain the displacement and the force from each signal, from each pillar. And we obtain the velocities of each of the pillar just by obtaining the gradient and by doing some filtering. And here we see the tangential velocity for one of the pillars in one of our tests. And we wanted to compare the tangential velocity of each of the pillars with the center pillar, which is the pillar under the highest normal force. And it's going to be the one that's going to stop moving at the end in all of our tests. So here we see how this first pillar stops moving, and then is the center pillar the one that finally stops its movement. So by tracking this relative velocity between each of the 8 pillars against the center one, we'll be able to detect this slip. So as we can see here in this bottom plot, this dot in yellow is our slip detected by the algorithm, and then the other one is the one that we detected with the camera. So we can see how we can detect this slip shortly after it's happening in reality. And here is just an example of one of our tests. So we have here our 3x3 array with all our different silicon pillars. And here we're just looking at those camera positions, reference positions. And we can see this difference in the time where the slips are happening. So what I was mentioning, this design of the sensor promotes incipient slip to happen. So we'll be able to detect the slip happening in the outer pillars before it occurs in the center one. So here we have 3/4 of a second between the first and last slips. Here we take a look at for the same test what our algorithm was able to detect. So a detection is a slip instance is detected when the tangential velocity drops below 50% of the tangential velocity of the reference pillar. So here we see the 50% mark, and we can note that we can detect slip in all the other pillars. Well, but we cannot detect it for the reference as we are using that pillar as a reference. And here for the test that I just presented, I wanted to show the timeline. So here in the y-axis, we have all our 9 pillars. In the x-axis, we have our time for our test. And in red, we see the reference, so the camera detected. In blue are the algorithm detections. So as we can see, we are able to detect slips shortly after they are occurring in reality. But also what we want to be able to detect is the ability to be able to detect incipient slips. So to detect this slip before the last pillar starts slipping, and then that would mean that the object would start falling. So here in this box plot, we're just seeing that time between the first and the last slips. So we see how when we increase the velocity, this time will shrink, we get shorter. And to evaluate the effectiveness of our algorithm, we wanted to take a look at this time difference between our detection and our reference. And this is what we see here in this box plot for all the different velocities. Actually, at really low velocities, we get a lot of variability due to the noise in this velocity signal, since we are not applying such a filter with a very high window size, because then that would add a lot of latency. But here we can see how our algorithm had a precision of 83% and a sensitivity of 82%. And we also wanted to take a look at the ability of our sensor and our algorithm to detect this incipient slip. So we looked at the time difference between gross slips, so the last reference slip, and our first detection. And this is what we see here in this box plot. So we can observe how all these values are giving us a positive time difference. So this means that for all our tests, we were able to detect this incipient slip. So this means that we would be able to adjust our grip force and to avoid the falling of an object when we deploy this into a gripper for real object manipulations. And finally, so since the submission of this paper, we've made some progress. So we've actually repeated this test, but increasing the tangential velocity up to 16 millimeters per second. And we also tested our algorithm on rotational movements and also translational plus rotational movements. So here we see an example of rotational movement in the clockwise direction. So we see how we detect the slips first in the outer pillars and then in the center pillars. And finally, our future task, they would be to demonstrate this algorithm's real utility on object manipulation tasks. So we would place our sensor into a robotic gripper with a robotic arm and do some different object manipulation tasks. So we can demonstrate this developed algorithm. And this could be all from my presentation. Thank you for your attention.